A student rubs a plastic comb with a dry cloth to give the comb a positive electric charge. Figure 6 shows the charged plastic comb picking up small pieces of paper. Explain how rubbing the comb with a dry cloth gives the comb a positive electric charge. So here we have two insulating materials. They have electrons which can move and protons or positively charged particles which cannot move. At the moment they are both balanced. They have no charge because the negative charges balance the positive charges. When you rub them together, the electrons will move because the protons are fixed. The electrons will move or transfer from one to the other. And what you'll end up is with an equal and opposite charge on both objects. So for example, just in this simplistic example, 2 electrons have jumped here, making this giving this a 2 negative charge because there's 2 more negatives than positives, so 5 negatives and 3 positives, and this one has lost 2 negatives. So what this has lost, this has gained. So this has a 2 positive charge because there's 2 more positives than negatives. So explain how rubbing the comb with a dry cloth gives the comb a positive electric charge. Well, firstly, friction between the cloth and the comb. So you're saying what you do and then why you get the effect you do, because it's an explain question. Negatively charged electrons transfer from comb to cloth. So friction causes negatively charged electrons to transfer from comb to cloth. And this leaves an excess positive charge on the comb. So friction between the two, rubbing together creates friction. Negatively charged electrons transfer from comb to cloth. And remember, you have to say that because it says gives the comb a positive charge. So you have to assume, even though electrons could move either way, in this example, they've left the comb giving it a positive charge. If they move the other way, the comb would have a negative charge, leaving excess positive charge on the comb. And that's important as well, because there's always positive charge on the comb. There was before, but now there's excess. There's, in relation to the number of negative charges, there's excess. There's more positive charge. So while this question is quite easy to understand, it's important you get your language right. Look at this word excess and make sure you're paying attention to the fact it's positive so you know which direction the electrons are moving. Explain how the positively charged plastic comb picks up the small pieces of paper. So what happens is you've got a positively charged comb, and you can assume that these pieces of paper also had a neutral charge, balance of protons and electrons. As you move it closer, the electrons are attracted to the protons or the positive charges and move towards the surface of the paper. So a charge is induced, or a negative charge is induced in the paper. So it's basically created by the movement of the comb towards it. So you say negative charge is induced in the paper on the surface near the comb. So it's not like you've actually changed the number of electrons. They're not leaving. There's no imbalance here. Overall, there's still a neutral charge, but near the surface now, there's a relatively more negative charge, which is being induced by this comb with its positive charge moving close to it. And then finally, you finish by saying an opposite charges attract. That will explain why it can pick up the small pieces of paper. So remember, 3 marks, 3 points. Always use bullet points. Okay, so now we look at electric fields. Which of these diagrams shows the shape and direction of the electric field around a positive charge? Well, positive charge, you always have field lines moving from positive to negative, so that's what you should get moving outwards. These are field lines for a magnetic field, so these are completely wrong, and this is the wrong direction. Figure 7 shows 2 metal spheres. Metal sphere A is fixed to a table, metal sphere B can be moved. So this can be moved, this is fixed. Metal sphere B is placed at a short distance from metal sphere A, so they're close together. Both spheres are insulated from the table and given a negative charge. The force between the charged spheres is measured. Explain in terms of electric fields why a force is exerted on sphere B. So if you draw the field lines showing the electric fields on these spheres, you'd see that you have field lines coming into both, but they would overlap. And it's because they overlap, they interact with each other. So when field lines interact, whether it's a magnetic field or an electric field, a force is exerted on the objects. So explain in terms of electric fields why a force is exerted on sphere B. Both spheres have electric fields which overlap, that's the key thing, so they interact with each other. When they overlap, they interact, and that's what creates a force. Sphere B is moved and the force between the spheres is measured at several distances. Figure 8 shows a graph of force on sphere B against distance between the centres of the spheres. Describe how the force on sphere B varies with the distance between the centre of the spheres. So this is kind of one graph which actually I'd be tempted to explain backwards because it's just easier that way. So as the distance between the centre of the spheres decreases, so from 20 to 18 to 16, you can see the force on sphere B increases, at first gradually, but eventually exponentially. A rise like this is called an exponential increase, where it just gets greater and greater and greater. So you'd say, as distance between the spheres decreases, force on sphere B increases exponentially. So you're linking the 2 points together.